First off, I want to thank you everyone for coming out and logging on. The presentation will move forward with everyone on mute. As you have questions, please email them through the GoToMeeting system on the right. If you enter your question into the text box, we'll get the question and Lance will sort through them while we're going through the web presentation. Again, thanks for being here. This is Chlorinated Solvents, a summary of source, fate, transport, and remediation techniques presented by W&M Environmental Group. I'm Andy Adams with W&M Environmental Group. I'm a senior consultant and I'm the regional manager for the Gulf Coast. I'm a bit of a rarity in this business. I've worked with W&M for going on 11 years. And outside of research opportunities before this, W&M has been my only employer. I have a BS in Environmental Studies from the University of Kansas and a master's from the School of Public Health from the University of Minnesota. Most of my education, research, thesis, and professional life have revolved around fate, transport, and degradation of environmental pollutants and the interaction they have with exposure, risk, and effects on human and ecological health. As you might guess with those interests, I spend a large amount of my time working on what I like to call integrated site closure, which really could be a code word for larger messes, complex mixed messes, multiple chemicals, multiple sources, multiple classes of chemicals in multimedia phases. We usually see these types of issues at industrial, petrochemical, chemical, and manufacturing facilities. These types of problems often use the rules that are in place to the maximum extent. And what I mean by that is that we get into using risk-based corrective action adjustments of the environmental standards, removal of non-aqueous phase liquids, which is really liquids that separate from water. We often call these NAPL, and often chemical or biological remediation or bioremediation. I really enjoy these cleanups because they have a number of moving pieces.
I'm Jim Flory. I'll also be assisting today. I'm a technical specialist with W&M, which is also the only firm that I've worked for. I'm a licensed professional geoscientist in Texas and Alabama and a certified professional soil scientist. I received both my bachelor and master's degrees from Texas A&M in the areas of soil science and environmental microbiology, respectively. My research was primarily focused on soil and aquatic microbiology mixed with geochemistry and hydrogeology, which I've been able to carry over into my current profession, which is environmental consulting. I like to think I have a somewhat unique combination of knowledge of the regulatory framework and the science behind it. And as a result, I like to utilize a number of tools that are offered by Texas's risk reduction program in order to provide effective risk-based strategies for site closures, which often incorporate various remedial techniques as well as mechanical and administrative controls. As a microbiologist, I like to allow nature to facilitate the contaminant remediation as often as possible, which many times requires some manipulation of the infected environment to maximize rates of bioremediation.
Thanks, Jim. So as we get into this, I'd like to take a look at historical usage of chlorinated solvents. There are many uses to chlorinated solvents. They're used in dry cleaning, fluorocarbon, and these are coolant and such type materials, the manufacture of those, solvent usage, fire extinguishers, heat exchange mediums, chemical intermediaries, extraction of caffeine for all the coffee drinkers out there, degreasing, parts cleaning, engine and brake cleaner, cleaning circuit boards, aerosol propellants. That's one of the many things that can make potentially make used aerosol cans a hazardous waste. Foam plastic blowing agents and paint removers. This is just to name a few. On the bottom, that's a picture of the coffee decaffeination process. It's really quite a nasty process. Circuit board cleaning mixed with acid for etching is also not a pretty process. So why can we use chlorinated solvents for all of these uses? Pretty amazing compounds if you consider the broad uses. Just consider chlorine wasn't identified until 1774, but it's been used for millennia to keep food disinfected. Someone might ask why I have a leg of prosciutto on the slide. Well, it characterizes chlorine's use pretty well. It's a preservative like no other, the salt that was used to work the prosciutto. But that can also be a bad thing, as we'll find out as we move forward. Chlorine is heavier than hydrogen and much larger, which is why we use it in the way we do. Being larger and heavier than hydrogen means that chlorine-containing compounds are exceptionally different from water-based compounds. Two of the first discovered chlorine compounds were DDT and PCE, but not until the early 1900s. The two distinct compounds share the special characteristics that we just discussed. PCE, perc or perchloroethylene or tetrachloroethylene, all the same chemical, is a dense, hydrophobic, non-ionic solvent. That ultimately means that it helps to dissolve all the things that the other greatest solvent on Earth, water, does not. It's also heavier than water, which you can see if you look at just the relative sizes of the two compounds. The two dot plots that I have on the page, the red guy is water, that's H2O, 2 hydrogens. The green guy is PCE, 2 carbons, 4 chlorines. The green folks are the chlorines. You can see that it's a much larger molecule and it's also much heavier. DDT and other chlorine compounds exhibit the disinfection properties I mentioned. Too much disinfectant property can affect the central nervous system, which then gives you a poison. These are things like DDT, chlorobenzene, eldrin, dieldrin, chloridane. I just want to cover one important concept as we move forward here. The dense characteristic of chlorine enables it to not be miscible with water at high concentration, which means it forms a dense, non-aqueous phase liquid. We usually refer to this as, depending on where you're at in the country, DNAPL or DNAPL. This DNAPL basically is a separate liquid which separates from water and forms 2 layers. Water on the top because it's lighter, chlorinated solvent on the bottom because it's heavier. By far the most common use of chlorinated solvents in the U.S. has been dry cleaning. Dry cleaning is a process which we take PCE and we use its dense and hydrophobic properties to help clean non-ionic and non-hydrophobic gunk from our clothing. It also helps not to shrink natural fibers, the cottons and different things like that, like water can. The earliest dry cleaning with solvents started by French textile manufacturers who were using kerosene and gasoline. Given the vast health and safety concerns, that process didn't last very long, which led to William Stoddard creating the Stoddard solvent. The Stoddard solvent was less flammable, and it was a white petroleum solvent, which improved the cleaning powers. By the mid-1930s in the U.S., the industry, because of flammability concerns, the Stoddard solvent was still a flammable concern in buildings. Shifts over to the recently invented PCE or PERC, which is a better cleaning solvent. PCE is a relatively stable, low-cost, high-performance solvent that really cleans well. It's dense and it'll penetrate just about any stain. It turns out that becomes problematic because of the penetrating power and the denseness of the solvent. That combined with the toxicity when ingested leads to problems. PCE can and will penetrate feet of concrete. In very limited time, it quickly moves through many soils and into groundwater. A movement which is still occurring in the U.S. is the changing of PCE back to improved petroleum distillates. This is occurring currently in the dry cleaning industry. We'll cover the breakdown of PCE and the remediation potentials in a little bit. It turns out of all the chlorinated solvents, you'll hear a lot of talk will be centered on PCE. It is exceptionally popular. It should also be mentioned that the breakdown of PCE, if you have PCE, you also have some amount of trichloroethylene or TCE, dichloroethylene or DCE, and vinyl chloride or VC. One of the other large groups of chlorinated solvents also include products that are essential to many industrial processes. The most common chemicals used in these areas and processes are TCE, VC, DCE, trichloroethane or TCA, carbon tetrachloride, chloroform, dichloromethane, and chlorobenzene. Those are just to name a few. There are literally hundreds of compounds that are used every day in industrial settings. Chlorinated solvents are used in the workplace because they provide high performance at lower cost than most alternatives. They are especially used where water is not miscible or mixable with what they are trying to remove or clean. Again, because of the physical chemical processes involved with the chlorines associated with the solvents, these solvents are dense, they are hydrophobic, and they are relatively stable and break down slowly. They are exceptionally useful in the industrial environment, but in large amounts they can also be exceptionally toxic, very good disinfectants. And when we start mixing these qualities with the fact that they are stable and degrade slowly, they start to be a concern from a persistent pollutant in the environment. If we look at chlorine usage worldwide, by far the biggest use is in the plastic market, and I'm looking at the chlorine usage worldwide in 2013. It's the biggest use in plastics market for PVC specifically. Vinyl chloride is one of the chief constituents used in PVC production, but inorganic and oxygenates are also the next biggest usage, which also is for industrial uses in cleaning. Overall usage of chlorine is down for solvents used as dry cleaning because of the move away from PCE. In the graph next, in the middle of the screen at the bottom, carbon tetrachloride is often used as a precursor to look at overall chlorinated usage worldwide. And in 2013, we see the vast majority of the usage is in Western Europe, the U.S., and China. Not surprising given the industrial complex in those three countries. You'll see that industrial uses of chlorinated solvent do not only extend to private industry. That's a B-52 on the top. It flew through a mushroom cloud when there was nuclear warhead testing being done. And it's being decontaminated with gunk engine cleaner, which at this point in time contained TCE. For all of those of you into compliance, I don't believe they had a spill plan or likely a contingency plan at this point. At this point in time, gunk degreaser probably contains 5 to 6% TCE. Gunk is still around, and they have found an alternative use that uses ethanol and terpenes, and that's in the present-day gunk cleaner. And we'll get more into the terpenes here in a second. Down from there, you might first think that's L-napple or light non-aqueous phase liquid. But if you look carefully, you'll notice it's connected and there's product on the bottom. That's quite likely a bunker B or C. That's an oil cut with TCE or carbon tetrachloride. So you get some that floats, some that sinks, and even some in the middle. As you can see, it's attached. Just below that is D-napple with water above it. The water is a bit hard to see, and I'm looking at the white plastic container. The dark on the bottom is a D-napple, and there's water just above that. And then those are just some large heated dip tanks on the bottom. There are many other chlorinated compounds, and I don't want to get lost in the details, but I thought it was important to bring in the many other chlorinated compounds. Many of these are not normally thought of as solvents, and many are banned or not produced in the U.S. any longer. This group includes bis ethers, and those are common in plastics and intermediaries in pesticide production. The organochlorine pesticides like DDT, aldrin, dieldrin, lindane, and chlordane. It also includes banned and toxic persistent organic pollutants like PCBs, dioxins, and furans. Two special notes. This group would include the terpenes and isoprenes, which we discussed a little bit ago in the gunk cleaners. It's become an alternative to TCE. And terpenes are actually a natural product from trees. And quite honestly, I'd take terpene instead of TCE as it's a much less invasive chlorinated solvent. Terpene is only slightly chlorinated and elicits some of the good properties of the hydrophobic potential. These are the group that famously was discussed by then President Ronald Reagan as producing air pollution in the Appalachian region of the U.S. The term led to the concept of Reagan's killer trees, but it's a very real chlorinated, naturally occurring compound. Lastly, I'll point out dioxins and furans, while not a naturally occurring compound, are globally ubiquitous. Dioxins are the result of incomplete combustion of chlorine atoms, which means fire to products containing chlorine, and if we don't have complete combustion, we make dioxins. Many likely do not know, but 2,3,7,8 tetrachlorodibenzodioxin is normally referred to as the most toxic chemical on Earth. That's the model on the bottom. You'll notice again the green atoms are the chlorine atoms. Of course, famously, the use of DDT in the environment in the U.S. led to Rachel Carson's book Silent Spring, which is really the start of the environmental movement in the U.S.
So the next logical question, why or how do we let these chemicals known to be quite harmful enter the environment? And in the case of PCE and TCE, they're not actually consumed during their various industrial applications. They're not degraded or transformed as a fuel contaminant might be during combustion. And so as waste products associated with their use are disposed, PCE and TCE are released directly to the environment, often to the soil or to surface water. This could include waste generated through degreasing electrical or mechanical parts in the auto industry, or disposal of wastes generated by dry cleaning operations. If released to the surface, PCE and TCE will typically volatilize very quickly and or become photodegraded by the sun. Remember, these are volatile compounds. Once in the subsurface, however, they tend to be much more persistent and degradation rates are much slower, and oftentimes the release itself is actually occurring in the subsurface. PCE and TCE are both hydrophobic and both have densities greater than water, as mentioned. And as a result, they tend to readily migrate downward through the soil column until they reach groundwater, where they accumulate at the uppermost confining unit, as shown above. Once within the groundwater aquifer, contaminant migration will be dependent on the degree of bioremediation that's already occurred during the release, how much of the parent compound has been converted to DCE and VC, vinyl chloride, which are less dense and more soluble. What's the topography of the uppermost confining unit or aquitard? The DNAPLs, if they're present, will flow downhill according to the topography of the aquitard, unless, of course, they're directed by groundwater flow, provided there is sufficient groundwater velocity. Whereas DCE and vinyl chloride are obviously more likely to move with the groundwater gradient. PCE and TCE, if they're in the dissolved phase, will also move with the gradient, but again, if the concentrations are sufficient to produce DNAPLs, they may not move with the groundwater flow unless, again, the groundwater velocity is sufficient to carry them.
So the first question really comes back to why do we care if there are chlorinated solvents in our groundwater? And this answer comes back to the idea that if we drink groundwater impacted with chlorinated solvents, it may potentially pose a risk. Groundwater is really the most applicable pathway to being exposed to enough chlorinated solvent that it may cause human harm. In terms of toxicity, TCE and VC, carbon tetrachloride, and chloroform are all known carcinogens. PCE, DC, and the rest of the ethane and ethylene groups are suspected carcinogens based upon the proven carcinogenic power of TCE, VC, carbon tet, and chloroform. And so we should spend a little time talking about how we know these things are known carcinogens. To be a known carcinogen, there must be hard-based evidence. And we don't go around knowingly exposing people to these chemicals. The Hippocratic practice of do no harm always applies in situations like this. On the other hand, there are many unintended exposures, and so one of the most famous is the exposure at Camp Lejeune to more than 10,000 Marines to TCE tainted groundwater at low concentrations. And so TCE is a known carcinogen because of that exposure and because the cohort study that went along and found that it led to an increased incidence of cancer. The rest, PCE and DCE, are implied that they are carcinogenic because they are of the same structure and the same ilk as the TCE molecule. So this comes to the main point for the idea of risk-based closure. If the only issue is the prospect of the ingestion of groundwater, chlorinated solvents are exceptionally difficult to clean up. In fact, for the energy that needs to be expelled for cleanup, in many cases, Mother Nature is more efficient in cleaning them up through the natural attenuation of solvents by bacteria. I'm by no means implying that we can't clean them up quicker, but time and money are in direct competition for the cleanup of chlorinated solvents. So the idea of risk-based closure comes to limit contact with the groundwater. We can do this by installing an ordinance that does not allow the contact with groundwater in a manner that could cause the ingestion of groundwater. In Texas, this is often called a municipal setting designation, or MSD. It eliminates the most conservative pathway in the ingestion of drinking water, enables much larger concentrations to be left on site and still be protective of human health and the environment. A number of different criteria decided by the local district need to be satisfied in order to install this ordinance on a property. Statewide, One major requirement is that the property be served or be capable of being serviced by potable water from another source. And that really gets at the importance of having a drinking water source that is unimpacted. In an instance where an MSD ordinance isn't able to be installed, a plume management zone can be installed for a groundwater plume that is stable and has had the source removed. This type of risk-based closure requires that post-closure care can be instituted to ensure the plume remains stable. If groundwater concentrations are so high that risk-based remediation isn't able to be used, or if there are requirements that cannot be satisfied through the risk-based process, remediation moves to physical removal, chemical degradation, or enhanced biodegradation, which we'll get into as we move forward. In general, risk-based closure is cheaper than physical remediation, but sometimes there isn't a choice if an agency is telling you that you will remediate. I've always found this picture funny and ironic. It's a coin-operated laundry that had coin-operated dry cleaning machines that leaked. It was indeed an MSD coin laundry. After the assessment, source removal, and delineation of the property, it used the risk-based tools and applied an MSD on the property, which closed the ingestion pathway to the groundwater and in fact closed the site after the pathway was removed from consideration. This is Houston, and this is actually Houston's GEMS system. I chose Houston because they have the best graphic interpretation of how cities have used MSDs. These red properties are real properties that have MSD ordinances applied by the City of Houston, and the city actually keeps track of these for construction worker safety purposes and different things like that. And this is also on the east side of Houston, which has been heavily industrial. Again, these are properties that have had an assessment performed, have had their sources of chlorinated solvents removed, and not, by the way, not all of these are chlorinated solvent sites, but more than half are. Have also been delineated to the satisfaction of the City of Houston. So risk-based closure and MSDs and plume management zones are one option for dealing with chlorinated solvents. I really love to use this graph, and it takes a bit of explaining to really understand, so we'll spend a little bit of time here. It actually comes from my friends at Regenesis. I want to make sure I give them credit where it's due. It's a pretty old concept, but when I see this chart, it makes sense to me. On the y-axis, you have remediation effectiveness. I like to think of this as the return on investment type indicator. When the y variable is high, you're getting a lot of bang for your buck. When it's low, you're not. On the x-axis, we have decreasing contaminant concentration. So this is the amount of DNAPL or dissolved chlorinated solvent that is in the system. So DNAPL would be on the left on the x-axis, and as it changes and becomes dissolved, because there isn't as much concentration, that's when you get to the right of the graph on the x-axis. So physical removal, which would include technology like pump and treat and dual-phase extraction systems, is massively effective when you have high concentrations of DNAPL, and it decreases in effectiveness quickly as the concentrations of DNAPL decrease. This comes down to the concept of contact. If we're using a physical recovery method, there's got to be enough concentration to grab some of the DNAPL. So think of this like this. If you have a bucket and you could dip the bucket into groundwater, when it came out, if you could see some of the DNAPL you were trying to recover, it's still an effective tool. Once you look at the bucket and you can't see any more DNAPL, then it's time to consider changing method because your concentration is too low to use the physical removal process to be effective. Sorry about that. Some pictures. That's a pump in the lower right, pump and treat system, an MDPE on the left and in the center, and some DNAPL recovery pumps. Two things with this. Physical recovery is a grab type application. The bucket has to be able to grab a noticeable amount of chemical to make it effective. If you don't have DNAPL or you can't grab a large enough concentration of it, change methods. Second thing, and this is a rule of thumb, you need more than around 100 parts per million, depending on the chemical, to make physical recovery effective. Maybe that's 1,000 parts per million for things that are more water soluble, like vinyl chloride or carbon tetrachloride, and maybe that's 10 parts per million for things that aren't water soluble, more like PCE. Either way, if you can't see it being removed or you can't run a sample and see 100 parts per million being removed in your discharge water, then you might think it's time to change your recovery method. We're going to switch over to chemical remediation, and chemistry is absolutely a contact sport. You have to put the chemical into contact with the DNAPL or the dissolved concentration. And it is still higher than, the concentration is still higher than what's acceptable to ingest, but it's not high enough to physically force removal. And so back to our graph, as physical removal becomes less effective at lower concentrations, chemical treatment becomes more effective. Chemical treatment can be done in a few different ways. It can be done in situ, and it can be done ex situ. The real point of either method of chemical treatment is that you put a treatment chemical into contact with your chlorinated solvent. The main part is that the two must come to contact with each other to be efficient. It doesn't matter if it's an oxidizing chemical, a reducing chemical, a reactive gate. The two have to come into contact with each other to be effective. So when is chemical remediation useful? On the chemical side, these are some in situ chemical injections that we're doing, where you're taking a chemical and pumping it into the ground. You see some daylighting on the lower right-hand corner with a sheen on it. The chemical spreads out and comes into contact with our chlorinated solvent in the aquifer. It then destroys and removes the chlorinated solvent from the system. Chemical injections for chlorinated solvents usually are chemicals with high oxidizing potentials and then drive the aquifer to a reducing state after the oxidation effect has worn off. Some of the popular chemicals for this process include persulfate, permanganate, Fenton's reactions, and other peroxides. You can see ex situ type applications as well. This might include where you open up an excavation and sow chemical back into the soil at the soil-water interface or deeper. Chemical remediation is effective where you can grab where you can't grab a chemical anymore, but there's still a good amount of it present. Rule of thumb, it's less than 100 parts per million and more than 1 part per million. Pictorially, in the lower left-hand corner, we inject the chemical oxidizer into the subsurface through a monitoring well or an injection point, and we are counting on there being enough chemical that it comes into contact with the red dots of the chlorinated, the red dots that represent a chlorinated solvent. The blue dots represent a chemical oxidizer. There has to be contact between those two groups for destruction to occur. I'm going to turn it over to the microbiologist now.
Thank you, Andy. So as a microbiologist, I'd probably be just a bit remiss not to point out that to a degree we're speaking in some generalities. all project sites are somewhat unique. If you have sufficient contaminant concentrations such that physical removal is effective and efficient, it's always going to be a preferred strategy. That's not to say that you necessarily have to employ chemical means of contaminant degradation prior to consideration of bioremediation. Now, having said that, when contaminant concentrations become low enough or otherwise inaccessible to the chemical additive, we then become reliant on the microbial community to carry out the remainder of contaminant degradation. And so what are the concentrations we're talking about? We've pointed out that just generally, for a rule of thumb, less than 1 part per million. But they can definitely vary depending on the contaminant and the characteristics of the site. Chlorinated solvents tend to be a particular challenge because although 3 parts per billion with a B sounds like a very small number, which it most certainly is, it's still greater than the drinking water standard for vinyl chloride. So let's assume you've arrived at the conclusion bioremediation is your next step, your best option. What now? And the answer is you need to ensure your groundwater conditions favor the process you're hoping to achieve and are hospitable to the organism that's hopefully going to be carrying it out. Microorganisms live in every environment on this planet, but they aren't all adapted to live in all environments, which is what the cartoon at the bottom right is depicting. Some live in the depths of the ocean where geothermal hot springs occur. Some live beneath the ice caps, some in salt mines, in acid runoff, toxic spills, etc. In the instance of groundwater impacted with PCE and TCE, we typically need to create a reducing environment, an anaerobic environment. Some specific examples of groundwater amendments we use to achieve this include things like hydrogen release compounds, or HRC, molasses, methanol, lacto oil, emulsified vegetable oil, and even cheese whey. And of course, there are many more depending on your site conditions and the specific contaminant that you want to address. One of the most common bioremediation mechanisms for groundwater impacted by PCE and TCE is reductive dechlorination, or in this instance, dehalorespiration. Now, respiration is a necessary function of all living things. It's part of our metabolism. It's how we convert food sources into energy. Higher life forms on this planet, which includes plants and most humans, utilize oxygen during respiration. This is called aerobic respiration. Now, we are obligate aerobes. We have no choice but to use oxygens. For microbes, though, that's not the case. They can use all sorts of alternatives for respiration, which is considered anaerobic respiration, the use of anything other than oxygen. Some of the more common alternatives include things like nitrate and nitrite, sulfate and sulfite, and ferric iron. And incidentally, these things actually make very good indicators to determine whether or not your aquifer is in an aerobic or an anaerobic condition. And so again, a common bioremedial mechanism for PCE and TCE remediation is dehalorespiration, in which microbes reduce PCE and TCE through respiration. This is commonly carried out by members of the bacterial genus Dehalococcus. So the first step is to ensure that we have an environment conducive to anaerobic respiration, and we can help create that environment with the use of the aforementioned amendments. Further, we can determine the effectiveness of those amendments by looking at our aquifer's geochemical properties over time. Do we see reductions in concentrations of dissolved oxygen? Is oxidation reduction potential, or ORP, becoming increasingly negative? Do we see concentrations of nitrate and sulfate reducing? These are all secondary lines of evidence, often called MNA parameters, MNA being monitored natural attenuation. So when this process is occurring optimally, the bacteria are reducing our contaminants through respiration while consuming various substrates. Our primary line of evidence then is the reduction of our parent contaminants. PCE has 4 chlorines. It becomes reduced to TCE, which has 3, which in turn gets reduced to DCE, then vinyl chloride, and ultimately to non-toxic ethene. And in fact, Dihalococcus ethanogenus is a bacterial species which is capable of reducing PCE all the way to ethene. Unfortunately, it's the only known species capable of that complete reduction. So in this case, in this instance, with this remedial strategy, the products that we might be injecting into the aquifer aren't having a direct effect on the contaminants. Rather, the injectants are creating the conditions that optimize the process we hope the bacteria will carry out. This is called biostimulation. This differs from bioaugmentation, which is represented by the cartoon above, wherein you have some pristine lab-cultured bacteria being introduced into the harsh realities of the real world. And you can probably read the caption, "Oh dear, I didn't realize in the field would be like this. We should have stayed in the laboratory." Some microbiology humor for you. I know you appreciate it.
So just a quick review. When we look at groundwater remediation, there are multiple ways to go about it. Risk-based closure is by far the most efficient and effective if that's open to a site. Physical removal, chemical degradation, enhanced biodegradation or bioremediation are all acceptable outcomes depending on what you have. It's important to look at each site for what they are, where they're at, the regulatory framework that they're under, and how to move forward best, efficiently and effectively for both time, money, and the better outcome for human health and the environment. It was a pleasure speaking with you today. If you'd like a copy of this presentation, feel free to contact us, and we'd love to make it available to you. Additionally, if there are more questions you might have, we'll have a Q&A session now. Please drop us a line with your questions. Again, that's over on the right-hand side of the GoTo meeting. And if you'd rather ask them offline, feel free to contact us and reach out. We're always happy to take a look at sites to help out to give you some ideas with what's going on. And just so you don't think that we spend our weekends thinking about chlorinated solvents, both Jim and I have dates with Sweet 16 matchups tonight. So thank you, KU and Texas A&M, for the use of your logos. Lance, have you had any questions come in?
I have 2. A couple of them mainly are we going to be giving out the slides and recording of the webinar, and the answer is yes. As soon as we get done, I'm going to download that, and I'll send everybody a link so you can download the slides and watch the webinar. But yeah, we have 2 questions. How does Mr. Flory feel about bioaugmentation of bacteria to increase reductive dechlorination?
Right. So this is the direct addition of microbes to your aquifer, and I don't think you're going to find a lot of microbiologists who are going to recommend this method, certainly as an initial response. And part of the reason is depicted in the cartoon there. We probably don't think of it necessarily, but taking a microorganism and putting it into a completely foreign environment is basically akin to taking a human being and putting them on the face of the moon. although adapted to every environment on the planet, again, its microenvironments can vary so much based on a number of things like oxygen concentrations, pH, solute salinity, things like that. So certainly would not recommend that as an initial response.
Okay, excellent. And we had 2 more questions came in. Any thoughts on thermal technologies as a means of DNAPL removal, particularly in complex hydrogeological conditions?
That's an interesting one. I've seen some research on thermal and using DNAPL. Here's where the rubber meets the road on that. If you can't actively remove that DNAPL, it's going to be a long road ahead because there is so much mass sorbed. Because really, if you're heating, one of the things you're doing is increasing biological activity, which is great. You will start to break down things at a quicker rate, and you'll get more volatilization without a doubt. But when you're starting at a starting point of 10,000 parts per million, it's a long ways to get back to 1 or 2 parts per million where you have a chance at closure. But nonetheless, if it's really that advanced of a geology or hydrogeology, that might be your only outcome, in which case it will speed it up. But I think we're talking a pretty healthy, long timeline.
Okay, one more question. How long does it take on average for the chemical oxidation and biological oxidation? I know it will depend on concentration and conditions, but I'm trying to get a ballpark.
Well, I'll handle the chemical, and I'll let Jim comment on the biological. Chemical, most days chemical is fairly quick. So the actual chemical residence time is probably on the order of the quickest chemical is probably a Fenton's reaction, which is just a massive beat-down explosion of zero-valent iron and peroxide, and it's a couple days, whereas some of the longer chemical reactions are maybe 2 to 3, 4 weeks. But the big part there, you're going to experience rebound and you're going to experience other things, and it's really the aquifer coming back into some kind of equilibrium, or as a chemist I'd say steady state. You got to take some time for the groundwater concentrations and the soil concentrations to equal out. So while it might be a couple weeks for the chemical injectant, I would give yourself 4 or 5 months before I started deciding if it was truly effective or truly not effective, or how effective it might have been. And the more concentration, the more mass you removed, but the more concentration, the further you have to go. So keep that in mind as well. And I'll switch over to Jim to comment on the biology part.
Thanks so much. So the short answer there is going to be that it depends. In the case of PCE and TCE, they're pretty readily reduced, but again, you're going to have conditions that favor that reduction. So it depends on the properties of your aquifer. What are your amendments to that aquifer? Have you had prior chemical treatment of that aquifer? So a lot of the chemicals that Andy's talking about using, they work great for degrading the contaminants, but they're absolutely harsh to the microbial communities. So I hate to cop out in that regard, but if the chemicals work in the order of weeks to months, the final biological degradation steps are going to work on the order of months to years.
and I'm going to throw one thing in there at the end. This is an area when you have, if you get down to the biological side and you have that moving and there's some time period that you're looking at, like Jim said, months to years, that might be a place where you might improve your odds by using a risk-based closure method with the biological or the bioremediation. It might speed your way to closure.
Okay, guys, I think that's all questions we have right now.
Great. Thanks, Lance. Again, the presentation will be available. Download it and watch it again if you're that excited. And thank you all for attending and listening. Have a great day.